Okay, so let's begin. So we kind of started to introduce this topic a little bit, and we did it sort of sneakily in lab. So if you remember correctly, we were struggling to get the synchronous motor to start when we had the excitation winding energized, meaning the switch was in the closed position. What we found is that, excuse me, is that when the switch was in the open position, it actually would spin and rotate, but it operated at a lower speed than synchronous speed. I think most people got around 1760 or so RPM, where we expected a synchronous machine, because that's when the name, it runs actually in sync with the electrical frequency. With the lab machines, they were 4-pole machines, so we expected them to operate around 1800 RPM. But it was interesting that it would run at 1758 RPM, regardless of the amount of load that was applied. So, or it would actually reduce a little bit. So what that concept is based on is actually based on an induction motor. And so we talked about something called damper windings. Well, damper windings are located around any quality made synchronous machine. And they basically are smoothing units to help smooth out the operation of the synchronous machine. And essentially, it almost operates like an induction motor, where you have an induced magnetic field on the rotating part. So in a synchronous machine, we actually provide a DC field onto the rotating part. In an induction machine, we still need a magnetic field, but what we do is we induce that actual field. So we'll find that that induction motor is going to be the one where we really will see the flexibility that we have by getting that induced value, mainly because we can have variable speeds. So let's begin. So induction motors are by far, again, this is by far the dominant AC machine that you'll come across in industry. I would say 97, 98% of the three-phase machines are going to be induction machines. And notice how I said three-phase machines, because three-phase machines implies that it's an AC machine. If it's a DC machine, then obviously it would be three-phase. If it's a single-phase machine, like in your refrigerator, those actually would typically sometimes, well, I shouldn't say typically, but have you in the past would be induction motors. But if it's three-phase, it would definitely be an induction machine. So very easy to build, simple design. They're pretty rugged. I mean, obviously, if you put a lot of cheap parts in it, it's not going to necessarily be a good quality piece of equipment, but they're fairly rugged. They're designed to last for 20, 30, 40 years. Relatively low price in terms of what you get in terms of torque, output power, efficiency, as well as life. And they're pretty easy to maintain. For the most part, if you keep the area clean around them, so if you're not exposing them to any water or chemicals that could degrade the insulation, as long as the bearings are well maintained and your shafts are aligned, because one of the things that really destroys motors is if you couple a motor up to a load, if for some reason that load has a little bit of it's not perfectly aligned, if it can either go up or down in this position over time, that causes some bearing scoring, and you can get some damaged bearings that way. You can also damage the shaft. But if you do a relatively good job of aligning it, should last for years, and the maintenance on these things is almost negligible. I mean, if the bearings fail, you can sometimes replace them, but for the most part, they're pretty simple. And there's the only rotating part that you have to access is the mechanical shaft. From an electrical perspective, there's nothing that I need to access that's rotating. So I don't have to worry about getting power that's sitting there. I've got 3 leads ready to connect to my motor. And in the synchronous machine, I had to get that DC field from the stationary world to the rotating world, where in an induction machine, that doesn't exist because, again, that magnetic field is induced. And can anybody here think of another device that perhaps uses the concept of getting a magnetic field induced onto another section of the equipment? Can I pick on somebody more? You're first on my list. Do you have any ideas of a device that we've studied this semester that we're using some induction or something that is induced?
A transformer.
Very good. Yeah, a transformer is exactly correct. In a transformer, we have a current that flows in a primary winding. It gets a magnetic field that flows, and that in turn induces a current flow in the secondary winding because of that changing magnetic field. It's the same thing as an induction motor or induction machine, where we're going to induce a current on the rotating part, and that current is going to be an AC current. So that's the primary difference between an AC motor, an AC induction motor and an AC synchronous motor, is that the synchronous motor, you apply a DC field to the rotor, or you could use a permanent magnet motor. That's sort of the same concept. In an AC motor, it has an AC field. So DC field, synchronous machines, AC field, induction machines. Very wide power ratings. You can do fractional horsepower. Like I said, in your refrigerator, for your fan or your compressor, you can go with a single phase, a 32nd or an 1/8 of a horsepower. I have a hydroponic heating system, which is basically a forced hot water baseboard system. And they call these, and I don't know if anybody says this correctly, I say Taco. I don't know if that's the right brand, but these Taco, they're just pumps. They just circulate water through my system to transfer heat. And those are single phase. I think they're 1/8 horsepower machines. They go all the way up to 10 megawatts. The largest one that I've personally seen that like literally could put my hands on was 9,000 horsepower. And that's the largest induction machine that I've seen. That was for a reactor coolant pump at a nuclear power plant. So it would be 3 of those, and those 3 were responsible for circulating water around the nuclear reactor. Anybody seen a bigger induction motor? Probably not. That's pretty big. 9,000 horsepower is pretty big. But I bet most of you have seen something in the 5, 10, 50, 100 horsepower rating. Those are pretty common, especially if you've been in an industrial facility. So here's the key thing about an induction machine. The speed depends on 3 things. So remember, in a synchronous machine, it really only depended on the number of poles and the electrical frequency. So over here, it's 3 things. It's the frequency of the power source, same as a synchronous machine, the number of poles, because that determines the general synchronous speed. But the other part that it is a huge factor on it is the load of the machine. So this is what the advantage is of an induction motor. Remember, in a synchronous machine, it always wants to spin at synchronous speed. An induction machine will actually speed up or slow down depending on the load that that machine experiences. So, excuse me, sorry, I'm still hacking away here. I apologize for the annoying coughing and throat clearing. And whatnot. I tried a cough drop before class, but it doesn't seem to be super effective. But you can use what's called a variable frequency drive. And you can use that variable frequency drive, and that allows you to have optimal speed control. And when I say optimal speed control, I really am not talking about optimal speed. What a variable frequency drive does, it does control the speed, although you can have it controlling torque. But typically what you're trying to do is to torque. You're trying to actually have the mechanical load operate at specific speeds so that it can provide, a certain level of water flow. So most mechanical systems are over-designed. If you need 10 gallons, they'll design the system to do 12 gallons. And you'll just take that the extra gallon, and either you'll recircuit through the system, or you'll have a valve that could shunt it off. You would never be able to design a system that provides exactly what you need. So in a variable frequency drive, you can go ahead and just vary that value, that frequency or that speed, and then you can accurately control the water levels, that whatever you're trying to control. So variable frequency drives are far more efficient because a recirc line basically says, take water that you pumped into one location and send it back to where you took it from and just recirculate it. Not very efficient. You're just kind of redoing the process. If you put a valve, anybody know what another word for a valve is in electrical terms? What's a valve?
What?
If it's on off, yeah, but what if you can vary the position of it?
Like a transistor or
Or
a potentiometer.
potentiometer. That's what I was gonna say. It's a resistor, isn't it? It's a variable resistor, correct? And what do resistors do in electrical circuits when you run a current through them? What happens?
They heat up.
They heat up, exactly. So in real world, when you buy a valve, you actually have to, if it's control valve where you actually can vary the position, one of the things you have to be able to do is that has to be able to size to be able to handle the energy that that valve has to absorb. So if you're going from, I don't know, let's say you're going to 60 PSI down to 70 or 30 PSI, that valve is actually going to get pretty warm. So that's as long as you have a continuous flow in there. So it's the same thing with this. You don't have to use or lose the efficiency that is just wasted heat. So variable frequency is a much more efficient way to do that. And essentially, this variable frequency is how our electric vehicles work. So remember how we talked about Tesla? Anybody know what his key sort of invention was?
Wasn't it the induction motor?
Yeah, it's the Tesla motor, right? Or the asynchronous or the induction motor. So Tesla vehicles used to use Tesla motors or induction machines to go ahead and do that. They've changed to synchronous machines because of some efficiency, but the concept is they actually have. So when you push your accelerator down or up to get speed, you're just monkeying with this frequency. That's all you're doing. So same thing applies for induction motors. So how do you build it? It has a stator and a rotor, just like a synchronous machine. So this one has a little more detailed here because you can actually see how our rotor circuit is. You can go with a much smaller piece of equipment, where a synchronous machine, unless it's your car alternator, those tend to be much, much larger. It would be unlikely to see anything less than probably 15 to 25 kW in rating, where again, I could have a 2 horsepower motor, which is only 1.5 kilowatts, so I can get much smaller sizes. So you can see the stator here. This actually shows some of the slots. And then this right here, the string sort of just holds the winding in places. So you have stationary stator. This is obviously hollowed out with a rotor. You have a nice circular item. We have stacked laminations because we want to make sure we limit our eddy current losses. And we always have an even number of spaces, and it always has to be divisible by 3, because in the 3-phase machine, every time we add a pair of poles, we have to add a 3-phase set of windings. So if we were able to go through here and figure it out, we could count the number of slots, but you would be divisible by 3. Oh, somebody have a question? Hold on. Bear with me for 1 moment. Okay. All right. So we have our rotating circuit, and we have 2 basic designs. We have a rotor winding that has actual 3-phase windings. So remember how we talked about having an AC field on there. We have to have our AC capability, which means we need, if we have a 3-phase machine, we actually need to have a set of 3-phase windings on our rotor circuit. That's called a wound rotor machine. And you'll see those are used in wind turbines. So anybody familiar with the type of wind turbine that's been more commonly used in North America and perhaps even in Europe? That's, I believe it's the most common type that they use. There's a very specific title for it. Anybody want to guess? You can take a look on the internet, but it's called a DFIG. It's a doubly fed induction generator, which is basically all that is it's just a wound rotor machine. So you have these 3-phase windings on the rotor circuit that you have to bring out through, you use a bunch of brushes and slip rings to go ahead and access those rotating parts. But it's a very similar design to my stator winding. You also can use the other design, which is the most common design, which is called a squirrel cage induction machine. And a squirrel cage induction machine, this is the most common one because all you have is you just have aluminum bars, and you might have some windings as well, but you just basically have some aluminum with some windings, and then those are all shorted together. So you still have that 3-phase set of windings, but you would go ahead and have it that way. And you use that to go ahead and get your 3-phase windings. So here's a squirrel cage rotor. So pretty simple. Not a lot of windings, not a lot of information to see. The wound rotor is different because if you look over here, you can see that I have three, these are called slip rings. And then what sits on top are carbon brushes, which will allow me to convey electrical energy from a stationary world to this rotating world. So they literally slide along. So what ends up happening, and it's really hard to see, I'm not even sure if you can see it, but each one of these would be wired out to the three-phase winding that exists on the rotor circuit. These wound rotor machines, you hardly would ever see them not that long ago, but now because of wind turbines, that you see these a lot. Now, so that begs an interesting question. Why not use a synchronous generator and a wind turbine application? Why would we use an induction machine for a wind turbine application? We talked about generation, and it tends to be, we said that synchronous generators are the dominant source of electrical energy in the world. Why would the wind turbine manufacturers come up with a concept of using induction generators? They're trying to be difficult?
They have variable input speeds.
Yeah, very good. How fast is the wind? If the wind is blowing at perfectly the speed, you can get those blades to spin at exactly the right speed. So at a certain speed, right, we have the number of poles, we actually will step that up directly to 60 hertz. But how often is that wind at exactly the right speed? Almost never. So what ends up happening, you have to rotate at a higher speed. And remember what we said, the synchronous machine only will put out 60 hertz when it runs at, let's say, 1800 RPM. An induction machine works perfectly fine at 1800 RPM, and it can run at lower speeds than that if it's a motor. No problem, no problem whatsoever. So that variable speed capability is why they use that. They still will output 60 hertz, but they don't have to spin at synchronous speed. So that's why wind turbines have been using doubly fed induction generators. And we'll talk about why it works so well when we get into the more details of the construction. So here's the sort of cutout view from here, and you can see the slip rings. You can see the brushes over here. Anybody know what this element is right here?
It's a spring.
Very good. You're on, Nate. That's a spring. It doesn't look like a spring, but if you understand metallurgy, you can bend metal and you can heat treat it. And so this actually was bent at a certain, and it's attached here. So it actually maintains a fairly constant spring constant or tension over time. And the reason why you do this is because, remember, this is carbon. Carbon is very soft, and that's a good thing because you want the carbon to wear down. You don't want this slip ring to wear. So nothing is perfectly polished. Over time, there's going to be some wearing of this carbon brush because this slip ring is not perfectly milled. You're going to have some resistance. And I want to replace the carbon brushes way before I replace my slip rings. And if you take a look at older, and I say this older, but cordless drills or something like that, if you plug it in, sometimes you can look at it, you can see some sparking if it's an older drill. That's because the brushes on there have started to pit to the point where you're getting some arcing between the stationary part and the rotating part. Okay. But here is the connections here. And you can see you have the three-phase windings over here, but you can see the laminations. You can see the stator windings, and this one you can see the rotor windings. This one also does something called fractional pitch. We probably won't cover that this semester, but it has to do with producing a more sinusoidal output or producing a more sinusoidal waveform to get smoother response. And if you look really closely over here, these are bearings, right? So this is where you would actually keep the shaft in the center. So there's a bearing here and a bearing here, and that's all the support that has to stay in that location. You also notice over here that there may be a bearing located at this point, because one of the things about motors is they will actually start to move over time. They will actually start to get out of position. So you actually have to maintain a bearing on one end. It's called I think it's called an axial bearing, which sort of keeps it from basically walking out of the shaft or having this thing continue to move so that it impinges upon something here. All right. So this is the important part of this discussion for today, which is understanding the principle of operation. And it's a pretty complicated way of understanding it. But you think about it and hopefully it makes sense. So we know we have a rotating magnetic field. We went back to, I think it was chapter 4, where, or maybe it's chapter 3, where we had a 3-phase set of currents that produces a rotating magnetic field. And it's perfect magnitude. It never varies by 1.5 times any individual magnetic field maximum. And it stays constant. And we want that constant magnetic torque, magnetic field, so we can get a constant torque. So that magnetic field is there because we provide a 3-phase set of AC windings. Now, here's the difference between the synchronous machine and the rotor machine. So that AC field, or that AC current, is creating that magnetic field, exactly the same for a synchronous machine. The difference over here is in our stationary, or our rotating, I shouldn't say stationary, our rotor, which is this part right here, we see a magnetic field because we have a current flow in here, and that current flow through this iron is going to produce a magnetic field seen by the windings here. Well, I have a set of windings that sees a changing magnetic field, which in turn is going to get an induced voltage on those windings. Because I have a closed loop, it's a closed path here, the magnetic field is changing, I'm going to induce a voltage across there. And because the windings are short-circuited, you get a current flow. So ultimately, you really get a current flow, which produces the voltage. And that's why these have to be short-circuited, whether it's wound rotor or squirrel cage. If it's wound rotor, it's not necessarily short-circuited, but it's sent back to something external, which allows current flow to flow. Okay. So in a wound rotor, it's not 100% induced, it's provided externally. In a squirrel cage, everything is induced. So that's the major difference that we have here. That rotating magnetic field cuts the rotor windings. The changing magnetic field induces a current in the rotating winding. And that's induced in a 3-phase set of windings on the rotor. So just like in the stator, where we had a 3-phase set of currents that produces a balanced rotating magnetic field, we're going to set up our rotor winding to be very similar and produce a 3-phased balanced set of windings that's going to produce a nice constant magnetic field. So this rotor current is where we get our magnetic field. Huge difference between a synchronous machine and an induction machine. In an induction machine, our magnetic field is provided from the DC element or a permanent magnet. In an induction machine, our magnetic field here, get this, is induced, right? Induced from the stator windings, just like Mort said with the transformer. So why is it called an induction machine? Because the rotor magnetic field is induced because of the stator current flow. And then once we get to that point, we have two magnetic fields that interact. This equation, this torque induced K, B, R, B, S, it doesn't matter if it's a synchronous machine or it's an induction machine. At this point, now we have a magnetic field. We're going to go ahead and get a torque. And that's the basic principal operation of an induction machine. We're going to get operation because of that induced magnetic field. And it's going to run and rotate because those magnetic fields want to line up. All right, so again, another really important feature. Does a synchronous, an induction motor, let's say I have an induction machine and I want to connect it to a 60 hertz system and it has 4 poles. I would like that machine to run at 1800 RPM. Can I run it at 1800 RPM? Anybody want to guess?
They don't, but I don't know why.
Okay.
Unless it's the lag produced in the magnetic fields.
Keep going.
Well, the one that's induced, they're going to be spinning at different rates.
Are you sure about that?
No,
Okay. How about this? Everybody see the poll? Only three more people. One more. All right, that's pretty good. All right, so the answer is no. 62%. Yes. 38%. And the answer is maybe. Sorry to disappoint you. So it can run at 1800 RPM, but only if somebody's pushing it. Okay, that's the tricky, sneaky part. What happens over here when I have a rotating magnetic field that cuts the rotor windings? How do I induce a current in those rotor windings? Don't I have to have a changing magnetic field? So this rotating magnetic field that's spinning around, it only induces a current in the rotor magnetic field if it's changing, right? We talked about d phi dt. Well, if the rotating magnetic field is spinning at 1800 RPM and the rotor itself is spinning at 1800 RPM, it's like you sitting on the top of the earth. I'm sitting on Earth and I don't notice it's spinning along at 1800 RPM. But if I'm watching from a different location, I can see it spinning. Or if I'm watching at something that is running at a faster speed, I can see the speed differential. So technically you can, but it's only if you do an external prime mover. But the reality of the question is any induction machine will never operate at synchronous speed, because at that point it's just a rotating hunk of metal. It's not actually operating as a motor or a generator. It's just a big piece of metal. So if you take a look, remember our data sheets where we looked at some nameplates and we said, what is the speed of operation? And we looked at a bunch of data points and we saw that the speed of operation was 1781 RPM, 1752 RPM, and all that stuff. The synchronous speed on those machines is 1800 RPM, but the actual rotating magnetic speed is going to be less if it's a motor. If it's a generator, it would be higher. Okay, so that's how you can take an induction machine and make it operate as a motor or a generator. We can have a speed, we can operate at a faster speed, which means we're pushing it, right? So we're making it go faster than the rotating magnetic field, which means we're dragging it along. That's how it becomes a generator. If it's going slower, it's a motor. So it can never run at synchronous speed if you want it to actually operate as a motor. You always have to run it at a slower speed, again, if it's a motor, so you can get that changing magnetic field. Okay, does that make sense? No relative changing magnetic field means no current flow is induced because you don't see a changing magnetic field. And once you get to 1800 RPM, the current goes away and then the speed starts to drop. Once the speed starts to drop, you get a current flow, it increases back up, and then you go ahead and you get it operating that way. All right, does that make sense? Pretty important characteristic to understand. This is the operational speed. So be careful. This is how the mechanical speed will operate. This is the actual shaft speed, because we're going to look at different speeds here in a bit, and those speeds will vary. This speed is going to be mechanical speed. Okay, make sense?
conceptually, yeah.
Okay. All right. So because it doesn't actually run at synchronous speed, we will develop a concept to describe the difference between its operational speed and its synchronous speed, and that's going to be called slip. So the slip speed is essentially the difference between synchronous, and mechanical. So slip speed is the difference between these two. Pretty simple, pretty easy. But the actual more useful term is our parameter S, which is our actual slip. And our slip is going to be equal to the slip speed divided by the synchronous speed. So it's basically a ratio of what the actual speed of operation is versus the synchronous speed. And we actually have more than these two extremes, but if it's running as a motor, we'll pretty much have these two values here. What happens when the slip is 0? When S equals 0? How would you describe something that has a slip of 0? What's another way to say a slip of 0? Conceptually, perhaps.
Things aren't moving relative to one another.
Yeah, it's not slipping. It doesn't slip. So it's running at synchronous speed. If it's possible. So if slip equals 0, it runs at synchronous speed. If it's fully slipped, meaning that the speed, this difference in speed between the actual mechanical speed and what the synchronous speed is 1, then what's another way to say this? It's not rotating. It's stationary, right? Because this would have to be, for this to be 1, that has to be 0. N sync divided by N sync is 1. So the only way that happens is if Nm is equal to 0. This is called a locked rotor or a blocked rotor condition when the machine is not operating. Okay, if you've energized it and it's not running. Obviously, if it's not energized, it doesn't really, we don't even really have to worry about it. But when we have it energized and its slip is 1, we go from there. And this is a unitless quantity, okay? Because RPM divided by RPM or radians per second divided by radians per second is going to be a unitless quantity. All right. So Mort was correct. An induction motor and a transformer are exactly the same thing. The difference is that in a transformer, we apply a voltage to our primary windings and get an induced voltage in the secondary windings. And we take that induced voltage and send it on, excuse me, and send it on down the pike to do, whatever it needs to do. So a transformer has to have a load to be able to move power through it. In an induction motor, the difference is that we apply a voltage to the stator winding that produces a voltage in our rotor windings, but we don't actually send that power electrically downstream. We would send that mechanically. So what happens in our rotor is now we've converted from our primary to our secondary winding. In the transformer, we're going to go from our stator windings to our rotor windings, which means we will cross the air gap in that motor to transfer our power from primary to secondary or stator to rotor. So why is that a similar concept? Well, because it's primary, secondary, stator to rotor. It's the same concept. What we see here is in an induction motor, the secondary windings can rotate. So when you think about something in a transformer, what's the electrical frequency going to be on the secondary of a winding? What would you guess is the frequency of the secondary windings?
Should be the same.
Yeah, 60 hertz, right? So here's what's different in an induction motor. Because the reference now is rotating along, and you have windings that are rotating, the frequency on the secondary windings, it's going to be AC, right? So it has a frequency, but it's not going to be the same. So your actual frequency is going to be not 60 hertz, and it should never be 60 hertz, because if it was 60 hertz, then that would mean you'd have a block rotor condition. The thing's not rotating, it's basically fixed. So if you think about the operation, this operates exactly like a transformer when it's not rotating. So can you think a little bit about how an induction motor it's taking a real beating when it's not rotating, because remember that rotor circuit, that rotor winding is short circuited. So if you didn't allow the transformer to rotate, if you locked it in position, you would burn it up, because you're moving all this power from a primary to secondary, and you have a short circuit in the secondary, you would generate a lot of heat. So one of the things you see is under blocked rotor conditions, you have to do motor protection, because you will burn up your motor pretty quickly. Except, and I learned this a long time ago, 20 years ago, is there an application when you would want to keep the motor energized regardless of how much current it was pulling through? It can never exceed what we would call the block rotor current demand. Would you ever want to provide the protection? Because remember, that piece of equipment is getting hot. What type of a piece of equipment, or what type of application, I should say, for an induction motor, would you perhaps want to allow a block rotor current to go indefinitely? Anybody want to guess?
Anything that requires a brake?
No. The application I'm thinking of is a fire pump. Would you want to trip the fire pump off because you're pulling too much current? Because the fire pump is providing water to help you fight a fire. Would you want to trip the pump off to protect the motor under fire pump conditions where you're running water to actually put out a fire? You probably want to let it go as long as you can. Who cares if the motor is damaged? We want to try to keep pumping water for as long as practical, until the motor basically will damage itself. But that's the only instance when you would actually go ahead and do that. So under life safety conditions, you can bend or break any rule. But the only reason why I found that is because I was doing some relay settings way back in the day, and I had to look at the National Fire Protection Agency. I think it was the NEC that has rules about you got to allow indefinite block rotor current in the case of a life safety piece of equipment like that. Okay, so frequencies are different. And back in the day, before we had variable frequency drives, if you had 60 hertz, but if you wanted to run something at 30 hertz, you would do with something called a rotary converter, which was basically taking an induction machine, and instead of short circuiting that winding, remember how we had that wound rotor? Instead of injecting AC current on it like they do for wind turbines, you would actually take that variable AC and then run that to loads. So you could look at rotary frequency converters, and you used to see them. They were pretty common because if you had single phase systems and you needed 3-phase, you would see these rotary converters that would do that. Now everybody just buys a variable frequency drive. So I don't even know if you can buy rotary converters anymore. But the last time I saw was at a nuclear power plant. That's actually how they maintain control of the control rods for the nuclear reactor. So that's how they get their power. If for some reason they stop spinning, the voltage goes away and it drops off. Again, I apologize for the coughing. I'm going to try to do another cough drop. Sorry about this. Trying to get along as best as I can. Okay, so all these equations were developed for our synchronous machine, but now we're going to tweak it a little bit. This is going to be equal to our rotor frequency, and that's going to be equal to the number of poles times our speed, and this speed is going to vary a little bit, divided by 120. And our n here is a way of putting this as our slip speed, our actual speed of operation. So our rotor frequency, if we substitute in our slip speed equation into here, poles times my synchronous speed, sorry, my slip speed minus my mechanical speed divided by 120. Then my actual substitution here, I have P times my synchronous speed divided by 120. This is the electrical frequency equation here, multiplied by S. So the actual electrical frequency can be determined by taking the rotor electrical frequency can be determined by taking the stator frequency, which again is 60 hertz, multiplying it by the slip, and that'll give us the actual rotor frequency. So it's very common for rotor frequencies to be 1, 2, or 3 hertz. So that's the actual AC waveform. That's the actual frequency on the rotor as compared to the 60 hertz on the stator. Okay. So very important to understand that these frequencies should never be the same if you're going to get operation. The most you're ever going to get is 60 hertz. The least you're ever going to get is maybe half a hertz if it's going to still operate as a motor. Okay. So what would the frequency of the rotor's voltage? Excuse me. How do we vary this? Then again, it's going to vary from 60 hertz to 0 hertz. Okay. All right. Let's answer these questions. We have a 3-phase 208 10 horsepower 4-pole 60 hertz machine. It's Y connected. We want to, and the induction motor has a full load slip. So this is the other thing too. When we produce full load on a motor, if you look at the nameplate of the motor, it's rated at 10 horsepower at a certain operating speed. It'll tell you what the speed of operation is. Another way you could write that is the slip speed, but more people are interested in what the actual speed of operation is. But remember, this is going to put out 0 horsepower if it runs at slip speed. I mean, at synchronous speed. So it has to run at our less than our synchronous speed. It has to actually run at the mechanical speed, which is the difference between synchronous or the slip, I should say the synchronous minus the slip speed. All right, so the first thing we have to do is figure out what is important to answer the questions. Well, for these first 3 right here, they all relate to either speed or frequency, which is essentially speed. So all I really care about is I need to know that it's 60 hertz. That's important. I need to know that it's 4-pole. And I need to know that it's 5%. I really don't care about 208 volts, and I really don't care that it's Y connected. So one of the things that you do as you get better at doing these problems is looking at a description of a problem and being able to sort through what is important to me and what is not important to me. Well, for the first 3 parts, I'm going to go ahead and I've got to figure out what is important to me. 4-pole, 60 hertz, 5% will give me the first 3 bits of that problem. The fourth problem is what is the shaft torque? So remember, power equals torque times omega. So at that point, we would need 10 horsepower, but it's only to get the shaft torque, what the mechanical engineers can use for either foot-pounds or newton meters of torque. All right. So our synchronous speed of operation for a 4-pole machine, and this is again just the order that where I recommend that you do that. You almost always need to get the synchronous speed or to calculate the synchronous speed. So we're going to go ahead and calculate synchronous speed. And for most of our problems, all you need to do is remember that table that we presented back in chapter 4, which is 3,600 RPM, 1,800 RPM, 900 RPM, et cetera, et cetera. Or if you don't like that, you can just memorize this equation. 120, the electrical frequency over the number of poles, will tell you that this speed is, it operates at 1,800 RPM synchronous speed. The actual speed of operation, so the mechanical speed, is 1 minus the slip times the synchronous speed. So this machine puts out 10 horsepower, which is its nominal rating, at 1,710 RPM. Our electrical frequency on the rotor, we find by taking our slip, which is 5%, multiplying it by our electrical frequency, 60 hertz, multiply those 2 together, and the actual frequency on the rotor, that's the electrical frequency, is 3 hertz. And then our last part, which is the output torque. So power equals torque times omega. We already represented that. Our load is our output power. Again, that's going to be converted to watts, divided by our rotational speed, preferably in radians per second. There are some equations that you can do things if you're in RPM or in horsepower, but we'll just go ahead and get those to the corrected units. So 2 pi nm divided by 60 is how you convert RPM to radians per second. So this particular machine can produce just under 42 Newton meters of torque. Okay, questions on that? Okay. Well, if there are no questions, let's look at what are called our torque versus speed characteristics. So this is, again, the beauty or the advantage of how we can operate or work with an induction machine. So any mechanical load has a way, or what's called a torque versus speed characteristic. It may not necessarily be developed in curves, but you can actually get data based on the size of the pump that you're doing, how much water it's pushing, and it's going to demand a certain amount of torque. Well, you want to be able to start that pump. So one of the things you have to do is you've got a motor that has water sitting on it, and it's got to be able to spin the impeller, or whatever the pumping system is. It's got to be able to spin that up. Well, that's pretty good if you look at this curve, and we can vary this curve characteristic or its curve shape. But for a typical, this is going to be, and we'll learn more about the NEMA design. But for a typical induction machine, we have a starting torque of about 2 times greater than its full load torque, which is important because, again, we're hitting this at no speed. This is our locked order condition. This is when the thing is pulling in a lot of current. It's not really putting out any torque, right? Because if power equals torque times omega, if it's at 0, then obviously it can't do anything. But over here, this is just after we leave 0. But it's able to put out 200% of its nominal value. And then it's going to increase until it gets to this maximum value, which is called pull-out torque. So this is the absolute maximum torque that this machine can operate at. That doesn't mean it can continue to operate for that indefinitely. Usually that's way over, because if you look over here, the machine is designed for a certain heat producing characteristic at a full load torque. So it can produce here and it won't burn up. It's designed to reject enough heat into the ambient environment to go ahead and not burn up at this value. So we want to get through this pretty quickly, and then we go down fairly quickly and we get to this value here where we're going to operate. So we start up, the machine spins up very fast because it's got a lot of torque capability. Once it gets past this pull-up, then the speed continues to increase, but the torque output goes down until our torque that is induced, or shouldn't I torque reduced, the mechanical output torque of the motor matches the load of whatever mechanical system is attached to it. So once it's reached equilibrium, that's someplace over here. And for what it's worth, if you buy a 10 horsepower machine, and you can talk to our mechanical engineering friends, 10 horsepower is usually more than what the mechanical piece of equipment needs. So you don't design a system that has 9.26 horsepower of load and design a 9.26 power motor. You just buy standard motor sizes and you say the next size up is 10. It's going to operate a little faster. That's generally okay, because most of the time, like if you're in a pumping application, once you start spinning faster and faster and faster, sometimes that power, that pumping speed will slow down because you're getting less efficient. If it's continuing to do that, your mechanical system has to just be able to design to handle that additional flow, or you put a variable frequency driveline. And that is the torque versus speed characteristic. And then hopefully what you can see here, anybody a fan of EVs at all? Why is a Tesla, $100,000 Tesla Plaid, able to beat almost any car in a 0 to 60 mile an hour test run?
Torque at low speeds.
Yeah.
Instantaneous torque.
Yeah. Look how much torque is available at basically no RPM. What about a car engine? Usually car engines put out their maximum power someplace, 3, 4, 5,000 RPM, sometimes right below the red line. So to be able to put out your maximum torque, your engine has to be spinning at almost the red line. If it's a reciprocating engine over here, this thing can put out all kinds of torque until it starts to get really close to its synchronous speed, and then it starts to drop. So if you've ever seen any of the YouTube videos where you see my Tesla versus, I don't know, Lamborghini, whatever, you see that the Tesla usually takes off from the line first, because look at all this torque. And then eventually, whatever sports car you have will be able to exceed and pass it if it's a long enough distance. But for the most part, electric cars have way more capability at 0 RPM. And I can actually design an electric motor pretty easily that this curve is almost flat. So I can change this characteristic until it starts to drop down over here. And I've never seen what the curves look like for typical EV, but works pretty well. All right, questions on that? Any questions on that? Well, let's jump ahead a little bit. Let's discuss a little bit of equivalent circuit, because it looks like I've got 23 minutes to go. So let's get into this a little bit. My voice, for the most part, seems to be hanging on. So remember how, again, we say this multiple times, but remember how an induction motor is basically a transformer. Why not use the equivalent circuit of a transformer? Go ahead and represent our induction motor. So this, if you go all the way back to your transformer circuit model, is an equivalent circuit, except for one difference. And the one difference here is, look at my secondary side of my transformer. It's short-circuited. So power comes in here, goes into the rotor circuit, and flows through here. And the idea here is that whatever power is converted to mechanically has to be represented with the resistor that's represented on this side. So our equivalent circuit is just a transformer circuit with the secondary short-circuited. That's all it is. Okay. So now let's go back over here. So the hard part about this is our turns ratio over here is a question mark, because we don't have a turns ratio that says I have 20 turns on the primary and 5 turns on the secondary, because part of this effective turns ratio is what is the relative speed of this is going to be. So it's usually far easier for us to go ahead and change this to be an effective turns ratio. And that's going to change based on our speed of operation. So if we can change this diagram to not be necessarily using those base values, but to base it on a parameter that we can use, like a blocked rotor condition, which we know we can block it, we can measure some parameters, we're going to go ahead and use that. So at our slip being 1, we're going to have our frequency is our maximum. So our induced voltage is going to be the maximum, because the dpdt is going to be the greatest when it's maximum. So we can write a generic expression for our voltage as a function of this maximum voltage under a block rotor condition multiplied by the slip. So this is a little bit of an extension, or a little bit of a guess, but we're saying that it's going to be linear about this operating point. So as the slip goes from 0 to 1, or I should say from 1 to 0, that our voltage that's going to be induced on our voltage is going to be a maximum, or the blocked rotor case, when it's not rotating at all, it's fully slipped, all the way to the point where there's no slip whatsoever, they're in sync, and there's no voltage that is induced. So that's what we're talking about here. That's our locked rotor condition. So our frequency is also the same case, where under blocked rotor conditions, we get 60 hertz. Under a machine that's operating at synchronous speed, we're going to go ahead and get no frequency there. So our frequency will use our equation that we developed. And notice our inductance. Our value of X here is going to be a function of omega, which if you drill down in a little bit, your omega has your electrical frequency here. In this equation. So omega sub L, 2 pi FL. So our rotor reactance here is going to change based on our electrical reactance. So if we use this as a block rotor value, we have a way of measuring X sub or X on the rotor. And it's going to vary depending on the frequency. So let us go ahead and use an X value that is based on our block rotor condition. And then multiply it by the slip that we experience here. Okay. So again, our rotor frequency is going to be a maximum when it's fully slipped. And it's going to go to 0 because there's no current. There's effectively no inductance associated with it when that's equal to 0. So here's our revised rotor circuit. And now everything is written as a block rotor condition. So here's our voltage. Here's our reactance. And our resistance doesn't change because that's not affected by frequency. So our rotor current is just going to be expressed in our updated values. So we can use Ohm's law, E divided by R, Z, and then we substitute in our block rotor parameters. Our block rotor condition multiplied by our slip, divided by the impedance, which is going to vary based on its slip value. And then here is our equation, just written as a function of our block rotor voltage here. And then now our impedance that is over here is R sub R over slip. So then we're going to change our rotor circuit to be a function here, because this is really useful for us because it tells us how much power is going to be available to machine, and it's based on the slip. When the slip is equal to 1, our machine is fully slipped, we're going to get lots and lots of current flow through here. When our slip is equal to 0, what does R divided by 0 become? It becomes a really big number, infinity essentially. So when we have our resistor here divided by 0, we have no current flow through this machine, so we have no power expansive there. So here is our revised sort of transformer equivalent circuit. And now we no longer have the transformer in here. And that's a good thing too, because we have no real way of getting this value. It's very difficult to get that. So we're going to express this without the transformer. We're going to have essentially our losses in our machine. So this is equivalent to our copper losses and our leakage losses over here. That's winding losses and leakage flux. We have a core and a magnetizing, just like we did in the transformer. Over here, we have some inductance in our rotor circuit. And what our R2 over S is going to be equal to is this is a load-dependent resistor. R2 over S is our load-dependent resistor. And our load-dependent means, or is indicative here because you're dividing by S. This value of S is load dependent. Remember, we went all the way back at the end of this slide, right? This curve here varied like this. This is our synchronous speed, but we just as easily could have redrawn this axis as a function of slip. Instead of going at 0, it would have been 1 to 0, but we could have gone through that way. So this is essentially writing that as a load dependent resistor. Okay. We'll stop here and have an opportunity for questions.
Paul, I have a question about actually previous subject, but it's probably going to pop up here. When we were doing the short circuit and open circuit tests on everything,
yeah,
you said that you can measure voltage current, which I can do all the time, but you said it's also easy to measure power. How is that
input power?
Yeah, how is like real power? How is that actually done to
You-
like what is used to measure input? Real power.
It's actually easier than you think. So
I imagine it might be, but is it like measuring RMS voltage over a known resistance or?
no,
Oh boy.
let me share my screen. So whoops. So these are pretty fancy. These are power quality meters. But you
Right.
can measure, this is power monitor. I'm looking for a very basic power meter for Fluke. This is power quality, but how do you measure power? You measure the voltage and the current, and you just get the waveform phase shift and it calculates watts. So like almost every electrical component that you have, you just measure the voltage and the current. And then you
Right.
get power.
But wouldn't that also be able to give you, if you know the phase shift, doesn't that get you your apparent power, like power factor?
Well, so that's just it. The newer devices they can actually calculate that.
Okay.
But what they used to do, that wasn't always available. So that's why a lot of the work we've done is just measure power. And keep in mind, some of these devices, if you're measuring, 1,000 horsepower motor or, 50 mega MVA transformer, you can't buy this, this is kind of expensive, $3,000, but you will get cheaper pieces of equipment that can actually measure power. So yeah, you can buy this on Amazon, and this is power quality. If I just want a basic power meter.
Yeah, I was wondering how like the basic ones only measure just real power, because I know that's what you said is like I have all of these, a lot of these meters that it can give you the phase shift. So
Yeah,
you'll measure apparent power going right into it.
Well, yeah, that's the advantages today, because you have microprocessor stuff that can easily calculate the phase shift, but it wasn't that long ago that you couldn't do that. So you'll just do voltage and current. And if you can pull out your angle, that just makes things a little easier. But if you have P&S, you can go ahead and do it anyway. So you can go from there. And it's not a huge step to calculate theta once you have your voltage and your current. Yeah, that's literally, you just set it up. You measure voltage across whatever you're trying to determine the power consumed. You measure the current in, and you're good to go. The other thing too, you got to be careful about phase shift is if you measure the phase shift, that's just the angle between the voltage that you apply and the current. So sometimes it can confuse you to say, hey, my voltage is this, my current is this, so this is the angle of the current. That's not necessarily the angle of the current. It depends on where your angle of zero is going to be. So sometimes your voltage is not at an angle of zero. So sometimes you can get yourself into a little bit of trouble if you haven't considered about where your reference voltage is. That's the B at an angle of zero. It's not super obvious if you're looking at a piece of equipment, but the thing I'm talking about is the grid. So you're down in Brunswick. If you were to go to Wyman Station, not Wyman Station, if you were to go to in Wiscasset, there's I can't think of the name of it's Mason's, Mason Station. They have a 345 kV line that is connected to the 345 kV line in Orrington here in Bangor. And the voltage angle for me or for near here is going to be different from what you are. So if you were just trying to put the current and say, well, I'm going to compare that current as a series current from Orrington, you'd lose the fact that maybe Orrington is a 0-degree angle and perhaps Mason Station is 3 or 4 or 10 degrees or something like that. So that's where you just have to be careful about calculating the angle, because it can trip you up to say, well, that's what the angle of the current is. Well, no, it's the actual angle between the voltage and the current. You have to make sure that you keep track of your angles the whole way through. If you want to learn more about that, there's something called synchrophasers that does a pretty good job on a grand scale to give you, what the overall phase angles are between point A, point B. You used to be able to look at those online, but now because of CEII and the terrorists getting, I guess, information about phase angles and all that stuff has been taken off the grid. But it used to be, I don't know, 10 years ago, you used to be able to go to Schweitzer's website and you could actually look at their website and you could see what was happening in Washington versus California, and you could look at phase angle differences, and so you could estimate what the power flows were going to be. But yeah, basically it. Okay, any other questions? Well, all right, my plan is to be back on campus next week. I should have no longer need to isolate, but we'll see how it goes. As you probably hear, I'm still experiencing some symptoms, but I am starting to feel better. I didn't have any chills yesterday, so a step in the right direction. Well, with that being said, if I don't have anything, have a great weekend. I'll see some of you on Monday. Take care, everyone.
Thank you.
Thank you.